So, let me illustrate how this is actually done. Now, there are, let me clear this off. There are situations where we try to test how certain elements belong to categories. So, we are sometimes we test for categories. So, let us write it chi-square test for categories. What do you mean by categories? Categories are sort of bins in which you can put elements. For example, the classical Mendel experiment in which he was crossing a tall variety of pea plants and a short variety of pea plants, and in the first generation all the plants were tall, and in the second generation when these plants were crossed with each other, he found that some are tall, some are short, and so the theory of genetics later predicted that it should be 2/3 to 1/3, 3:1 ratio, 3:1 ratio in which the tall variety and the short variety will appear. So, in this case, a particular plant is either tall or short, which means that it can be put in either this bin or that bin, put into this category or that category, and a theory predicts certain certain number of elements or experimental subjects being in a particular bin. It predicts another particular number to be in another particular bin. Then we apply the chi-square test for these categories. Okay. So, in that case, what are our expectation values? E is the expected value number in a bin, and O is the observed number in that bin. And since there can be different categories, this will be have to be subscripted by I. So, one can put in one category and then it would be E1 and O1, another category E2, O2, and so on and so forth. So, the theory will predict that so many will be in bin 1, so many will be in bin 2, so many will be in bin 3, and so on and so forth, and the theory will allow you to, or the test will allow you to check the correctness of that kind of a theory. But in that case, how do we define the chi-square? As we said that it is nothing but the E, I mean it does not really matter. In some books you will find O minus E, sometimes you will find E minus O, it does not matter because you are ultimately squaring it. So, it is O I minus E I square, and you need to normalize it by, otherwise you will not get the proper sense of how big is the error compared to what is the expected value. That is why you need to normalize it, and it is summed over I. Now, if you define this way, you are essentially saying that I have obtained a value and my expected value was this, and therefore, this is the fluctuation, this is the difference between the observed value and the expected value, that when normalized, that means we are essentially getting a sense of how big are the differences between the expectation and the observed value. This, if it is a if the theory is true, then these differences should be due to completely random fluctuations, and therefore, this whole thing should behave like random variables. And if then there is only one I, that means only one of these, then we will have to tally the behavior of only one random variable. If there are two of them, we will have to tally it with a combination of two random variables, that means y1 square plus y2 square, its character. If there are three such bins, three such categories, then we have to tally it with three of them, y1 square plus y2 square plus y3 square, how does that behave? And these things are available in the chi-square tables. Let me illustrate with an example. Okay, now let us go to an example. You know, there are certain characteristics in plants. For example, let us take the example of the pea plant, in which there are two categories like tall or short. That is regarding the height of the plant. And there is also another category whether the peas are round or wrinkled. That means the peas themselves are roundish or it is corrugated, wrinkled. So, these two characters we find, and we do not know whether these two characters are related in some way or other. But the theory of genetics says that if these two characters are independently assorted, how do I write? Yeah. Then, if you cross a tall variety with round seed, these plants are crossed with short plus wrinkled seeds, then in the first generation they are all tall plus round seeds. But in the second generation there are four possibilities: tall and round, tall and wrinkled, short and round, short and wrinkled. All of them appear, but in a specific ratio 9:3:3:1. So, if they are independently assorted, then they should appear in this ratio. Now, suppose somebody wants to test whether two such characters are truly independently assorted or not, and suppose she has conducted the experiment, she has chosen tall and round and short and wrinkled plants, cross them. In the second generation, she finds that there are all four possible varieties of plants. She counts them. She picks up some number of plants and then she counts them, sorts them and puts them into categories. Okay? And suppose the categorization is something like this. The result is something like this, that you have let me put it in form of a table. here we have the type, and there are 4 different types: tall, round, tall, wrinkled, short, round, and short, wrinkled. Right. Now, here we need to have some expectation and we need to have some observation. Okay. So, let me allow 2 columns. So, here the expected and here it is the observed. Now, what is expected? What is expected is the ratio should be 9:3:3:1. But you actually do not observe the ratio, you observe the numbers. So, suppose the total is 160 plants that she counted, and she observed 84 to be tall and round, 34 to be tall and wrinkled, 38 to be short and round, and only 4 to be short and wrinkled. That is what she found, and the summation is 160. Now, the question is, what is expected? What is expected is that out of if you add this up, 9 plus 3 plus 3 plus 1 turns out to be 16. So, 9 out of 16 should be should be tall and round. So, this I can you can easily see that 9 by 16 into 160 is equal to 90. So, basically whatever is the number, you have to multiply by that by 10. So, what is expected is 90 numbers should be tall and round, 30 numbers should be. So, these are the numbers that are expected. Okay. So, now on that basis we can go ahead and do the calculation. This also adds up to 160. 160. So, you see that there is a difference between the observation and the expectation value from expectation from the theory, but in spite of this difference, can we still say that the theory is correct, that these two characters are independently assorted? This is the question that we are asking. So, in that case we have to calculate the chi-square, and then the chi-square will be, as we have already seen, it is basically the observation I minus expectation I square by expectation of the ith value. So, this will be for the first one 90 minus I do not really care whether this one should come first, but let me write it that same way so that you are not confused. 84 minus 90 square divided by 90 plus 34 minus 30 square divided by 30 plus 38 minus 30 square divided by 30 plus 4 minus 10 square divided by 10. So, 84 is a observed minus 90 expected square divided by the expected value. So, we have calculated each one of them, each category, and then we have summed them up, and this number comes to be 6.66. Now, the question is that how do we use this, and for that we need to refer to the with the table. I'll show how to read the table, but the point is that we are trying to figure out whether they are independently assorted. We are trying to make the assertion with 95% confidence, and therefore, significance level of 0.05. So, significance level is 1 minus the confidence level, and therefore, we are trying to figure it out with a significance level of 0.05. So, we will have to read from the table, but now what is the degree of freedom? Notice there are 4 of these categories, right, 4 of these categories. So, a common sense would say that the degree of freedom is 4, so you have to consider 4 of them, but no, the point is that if you know the total number that you had started with, in total number that you picked up and counted, then if you know 3 of them, if you know 3 of them, you can calculate the 4. By adding this and subtracting from this, you know this one. Therefore, once you have obtained these 3, the 4th one does not have a freedom. There is no freedom to choose the 4th one. Therefore, the degree of freedom is actually degree, I will write somewhere else. The degree of freedom is actually n minus 1. Okay. So, in this case it is 4 minus 1, so 3 degrees of freedom. Now, let us see how would we read from the table. Now, here you can see the chi-square table, and for any value of the degree of freedom, these are tabulated here, and for each degree of freedom you have got a row, and the area beyond a certain value of chi-square is tabulated. What is tabulated is the area beyond a certain value of chi-square. So, for example, we are now looking for the significance level of 0.05, which is chi-square subscript is 0.05. It is this column that we are looking for, and we are looking for a row corresponding to the degree of freedom of 3. So, this row and this column, and here we have 7.815. So, the chi-square value is 7.815, beyond which the area is 5% of the total area, that means 0.05 significance level. So, this is the value that we are looking for, and if we have a chi-square value beyond this, then we would say that it is very unlikely to have that chi-square value coming out of a purely random variables, while if it is somewhere here below that critical value of chi-square, the critical value of chi-square, then we would say that we do not have sufficient ground for rejecting the null hypothesis. The table says that for this, the 0.05 level of significance happens at the critical value of chi-square for rejecting the hypothesis, in this case the null hypothesis, that comes out to be 7.815. I will show you how actually it is done. So, this is the value that you get from the chi-square table, and the value that you actually got from the experiment 6.66, which is lower. Lower means that the probability of getting this value is more than 5%, which means that we cannot reject the hypothesis. In this case, the null hypothesis is okay, this example I have not written the hypothesis and the null hypothesis. Let me do that, otherwise it will be a bit confusing. The hypothesis, the null hypothesis is that the categories are independently assorted, and then the alternative hypothesis is categories are not independently assorted. So, if they are independently assorted, then this would be the expected value. So, that is what we have written, and if they are not independently assorted, then it will be a different value. So, we are always checking for the equalities, and we would be able to reject the null hypothesis if the value of chi-square is beyond this value, but it is not, and therefore, we have to the null is true. We have to conclude that the null is true. There is not enough basis to reject the null hypothesis.